Welcome to today's paper reading. Today's paper is titled, Analytic-Splatting, Anti-Aliased 3D Gaussian Splatting via Analytic Integration. This paper was published on AR14 by Zhihao, Liang and colleagues from South China University of Technology and Tencent AI Lab. The 3D Gaussian Splatting, 3DGS, method combines the benefits of both primitive-based and volumetric 3D representations, enhancing the quality and efficiency of 3D scene rendering. However, 3DGS is not alias-free, leading to issues such as severe blurring or jaggies when rendering at varying resolutions. This is due to its treatment of each pixel as an isolated point, ignoring the area it represents. To address this, the authors introduce Analytic-Splatting, which uses a conditioned logistic function to analytically approximate the Gaussian integral within the 2D pixel window area. This method improves the intensity response of each pixel and makes the rendering process sensitive to changes in pixel footprint at different resolutions. Experimental results on various datasets demonstrate that Analytic-Splatting provides better anti-aliasing capabilities, resulting in more detailed and faithful renderings. 3D Gaussian splatting is a technique used for high-quality rendering that is both efficient in computation and suitable for real-time applications. Anti-aliasing is crucial in reducing visual artifacts, thereby improving the overall image quality and enhancing the realism of the rendered scenes. View synthesis, on the other hand, allows for the generation of new views from sparse data, which significantly enhances the richness and depth of 3D scenes. The field of novel view synthesis has seen significant progress due to advancements in neural rendering techniques. A prominent model in this area is the neural radiance field, NeRF, which uses ray marching for photorealistic rendering. 3D Gaussian Splatting, 3DGS, is another approach that offers a GPU-friendly, differentiable rasterization pipeline, enabling real-time, high-quality rendering. However, 3DGS faces challenges such as performance degradation when dealing with varying distances and resolutions, and it produces artifacts due to its insensitivity to changes in pixel footprint. Figure 1 illustrates the difference in pixel shading between 3D Gaussian Splatting, 3DGS, and Analytic-Splatting. In 3DGS, say, the shading of a pixel is determined by the Gaussian signal value at the pixel center, treating each pixel as an isolated point. This method can lead to aliasing and loss of detail, especially when the pixel footprint changes. In contrast, Analytic-Splatting B considers an analytic approximation of the integral over the entire pixel window area as the intensity response. This approach enhances anti-aliasing capabilities and preserves more detailed fidelity in the rendered images. The comparison highlights how Analytic-Splatting addresses the limitations of 3DGS by integrating the Gaussian signal across the pixel area, resulting in superior rendering quality. In the realm of neural rendering, techniques like neural radiance field (NeRF) have shown significant success in novel view synthesis. However, the backward mapping volume rendering used in NeRF poses challenges for real-time performance. To address this, 3DGS employs forward mapping volume rendering and GPU-friendly tile-based rasterization to achieve real-time rendering. Despite its advantages, 3DGS faces aliasing issues due to discrete sampling during shading. Anti-aliasing techniques, such as those used in MIP-NeRF and ZIP-NeRF, have been developed to mitigate aliasing in neural radiance fields. MIP-splatting introduces a hybrid filtering mechanism to restrict high-frequency components, though it may compromise detail preservation. Our approach aims to improve upon these methods by introducing an analytic approximation of the integral within the pixel area to better capture the intensity response, thereby achieving aliasing-free and detail-preserving rendering results. 3D Gaussian Splatting, 3DGS, models a 3D scene as a set of 3D Gaussians. Each Gaussian is characterized by a mean vector and a covariance matrix sigma, which is factorized into a scaling matrix S and a rotation matrix R. When transforming a 3D scene into 2D screen space, the viewing transformation involves an extrinsic matrix T and a projection matrix K. This transformation yields the projected position and covariance matrix sigma, which are used to calculate the 2D Gaussian signal G2D. This signal is essential for determining the volume transmittance and shading of each pixel, considering attributes like opacity alpha I and view-dependent color Ci. Figure 2 illustrates the integration of a Gaussian signal within a pixel window area and compares various approximation schemes used in different methods. The figure shows the ground truth integration, A, the baseline method using 3DGS, B, super sampling with 3DGS, C, filtering with MIP splatting, D, and the proposed analytic approximation method, E. Each method aims to accurately represent the intensity response of the imaging pixel by integrating the Gaussian signal within the pixel domain. The analytic approximation method, termed Analytic-Splatting, offers a more precise and efficient solution compared to numerical integration methods, providing better anti-aliasing capabilities and preserving high-quality details. In the 3DGS framework, the current approach ignores the window area of each pixel, leading to artifacts due to resolution fluctuations. To address this, an analytical approximation of the Gaussian signal within the pixel window area is proposed. First, the one-dimensional Gaussian signal integration within a window, x1, x2, is revisited. Monte Carlo sampling can approximate this integral, but it significantly increases computational burden with more samples. Instead, an analytical solution is sought using the cumulative distribution function, CDF, g, x, of the Gaussian distribution. The logistic function Sx is introduced as an analytical approximation of g, x, which can be scaled for Gaussian signals with different standard deviations. Figure 3 illustrates the pixel integration domain as described in EQ 12, and the transformed domain after rotation as per EQ 14. In Figure 3a, the yellow lines represent the coordinate axes of the 2D screen space, which define the original pixel integration area. Figure 3b shows the integration domain after rotation, where the yellow lines now correspond to the eigenvectors of the covariance matrix scaled by their respective eigenvalues. This rotation is crucial for simplifying the integration process by aligning the domain with the principal axes of the Gaussian distribution, thereby facilitating the approximation of the integral through independent 1D Gaussian integrals. The experiments focus on the approximation errors of the CDF of the Gaussian function and the one-width window area integral, both scaled by a factor of 1 times 10 to the power of -4. The results show that our scheme significantly outperforms other schemes in approximating the integral response. It is robust to different standard deviations and variable distributions, especially when the standard deviations are smaller. This indicates that our scheme is better at capturing high-frequency details. Quantitative results on the multiscale Blender synthetic and MIPNRF 360 datasets demonstrate superior performance in terms of PSNR, SCIM, and LPIPS. Figure 4 presents an error analysis of using our conditioned logistic function EQ 9 to approximate the cumulative distribution function, CDF, of Gaussian signals as defined in EQ 7, and the window integration as described in EQ 10. The approximation error function, ECDF, x, is defined as the absolute difference between the logistic function S, x, and the Gaussian function G, x. The errors are scaled by a factor of 1e-4 to make the differences more discernible. This analysis helps in understanding the precision of our approximation method in handling Gaussian signals, which is crucial for the accuracy of our shading techniques in Analytic-Splatting. Figure 5 presents an error analysis of approximating the window integral EQ 10, using various schemes as depicted in Figure 2. The figure illustrates the approximation errors for different schemes, comparing them to other approximation methods. It highlights the robustness of the proposed scheme to varying standard deviations of Gaussian signals, especially when these deviations become smaller, emphasizing the scheme's superiority in capturing high-frequency signals and details. This analysis is crucial for understanding the effectiveness of the approximation methods in handling the integral response over the one-width window area. Figure 6 presents a qualitative comparison between full-resolution and low-resolution, 1/8, images on the multiscale Blender dataset. All methods were trained on images with downsampling rates ranging from 1 to 8. The figure demonstrates that our method effectively reduces artifacts in 3DGS, maintaining higher fidelity in details compared to other methods. Figure 7 presents a qualitative comparison between full-resolution and low-resolution images on the multi-scale MIPNRF 360 dataset. The figure highlights that while all methods are trained with downsampling rates ranging from 1 to 8, our method excels in reducing artifacts and maintaining detail fidelity. Notably, 3DGS and 3DGS-SS exhibit significant artifacts at low resolutions, particularly on elongated shapes like wheels and flower stems. Conversely, MIP-splatting results in oversmoothing, evident in the loss of detail in areas such as lobes. Our method, however, demonstrates superior performance in preserving details and reducing artifacts, making it a more effective solution for complex scenes. Figure 8 presents a qualitative comparison of super-resolution, 2 times, on the multi-scale MIPNRF 360 dataset. The figure highlights the performance of various methods trained on images with downsampling rates ranging from 1 to 8. Notably, it points out the high-frequency aliasing observed in 3DGS-SS and the oversmoothing effect in MIP-splatting. In contrast, our method's results are depicted as being closest to the ground truth, showcasing superior detail fidelity and anti-aliasing capabilities. Table 1 presents a quantitative comparison of analytic-splatting against several cutting-edge methods on the multi-scale Blender synthetic dataset. The methods included in the comparison conduct multi-scale training and testing. The table highlights key performance metrics such as PSNR, peak signal-to-noise ratio, LPIPS, Learn Perceptual Image Patch Similarity, and SSIM, Structural Similarity Index. These metrics provide insights into the effectiveness of analytic-splatting in preserving image quality and detail across different scales. The results indicate that analytic-splatting performs competitively or better than the other methods in various resolution settings, demonstrating its robustness and efficiency in handling multi-scale data. Table 2 presents a quantitative comparison of analytic-splatting against several cutting-edge methods on the multi-scale MIPNRF 360 dataset. The methods included in the comparison are MIPNRF 360, MIPNRF 360 plus INGP, ZipNRF, 3DGS, 3DGS-SS, and MIP-splatting. The evaluation metrics used are PSNR, SSIM, and LPIPS, which are measured at various resolutions: full res, 1/2 res, 1/4 res, and 1/8 res. The table highlights the performance of each method in capturing high-frequency details and maintaining anti-aliasing properties. Analytic-splatting demonstrates competitive performance across all metrics and resolutions, indicating its effectiveness in handling multi-scale training and testing scenarios. Table 3 presents a quantitative comparison of super-resolution techniques at a 2 times scale applied to the multi-scale MIPNRF 360 dataset. The table includes PSNR, SSIM, and PIPS metrics for several methods, such as 3DGS, 3DGS-SS, MIP-splatting, and ours, across various scenes including bicycle, flowers, garden, stump, tree hill, room, counter, kitchen, and bonsai. The best results for each metric are boldly marked, showcasing the performance of each method in terms of image quality and perceptual similarity to the ground truth. In this paper, the authors introduce analytic-splatting, a method that significantly enhances anti-aliasing capabilities and detail fidelity in pixel shading. This approach achieves state-of-the-art results in novel view synthesis, particularly under multi-scale and super-resolution settings. However, the implementation of analytic-splatting involves more complex operations, which increases computational burden and slightly reduces frame rate. Despite this, the frame rate remains only 10% lower than that of MIP-splatting, another anti-aliasing method. The extensive experiments conducted validate the efficacy of analytic-splatting in various settings. Thank you for watching.